Hello and welcome to this lesson. Our topic for today is principle of mathematical induction. Mathematical induction is an important method to prove theorems concerning natural numbers or set of positive integers. Okay, so we all know that set of natural numbers are numbers that start from 1 up to infinity. Okay, that's set of natural numbers. Okay. And the method of proof. Okay. So in mathematical induction, you'll be given predicate statements. Okay. When we say predicate, let's cast our mind back on logical statement. When you say logic, it deals with statement and the relationship between them. And every logical statement is made up of two main types, either proposition or predicate. Proposition actually indicates whether a statement is true or false, and a predicate is mainly made up of variables. Okay, and we from here we can say that most mathematical um, rules or most mathematical statements are predicates. The outcome of these statements depends on the values of the variables. Okay, so when we say x and y such that x is less than y and x and y are real numbers. Okay, so let's pick any two real numbers x and y such that x is less than y. This is a predicate statement. Okay, but we can assign x and y by two values. Okay, so let's assume that our x is 5 and our y is 7. Okay, so when we choose 5 for x and y 7 for y, then we say that x 5 is what less than 7, which is what a true preposition. This time around is no more a predicate, but rather what preposition. Okay. Also, when we choose 3 for x and y for 1 for y, okay, but the predicate states that x should be less than y. But when we choose 3 for x and 1 for y, realize that 3 is actually greater than 1. Okay, and here we can see that this is what a false proposition. Okay, that's all for predicates. It's made up of variables. Okay, so when you have P of n be what a predicate statement about the natural numbers, then we have a proof. Okay, in the theorem of the form, for every natural number, we have what a predicate statement P of n. And this is actually made up of three main steps. We have the base step, inductive step, and the conclusion. Okay, the base step, we normally assign 1 to the variables. This is because set of natural numbers start with 1 up towards infinity. Okay, and the inductive step, we prove that if P of n, that's the predicate statement, is true, okay, then the next step, that is P of n plus 1, is also true. Or you can assume K such that K is what? Greater or equal to 1. Okay, and we say that if P of K is true, then the next step, which is P of K plus 1, is also true. That's the inductive step. Okay, so let's solve some examples. So this is the first question. We are to prove by mathematical induction that for every natural number, the series 1 up to n is equal to n multiplied by n plus 1 or divided by 2. That's what we have on the right hand side. Okay, so this is the first base step. Okay, so we choose or we set n to 1. Okay, so when we set n to 1, we have 1 equal to 1 multiplied by 1 plus 1 or divided by 2. And we know that we have, you see, the numerator, when you simplify the numerator, you get 2, and the denominator, you also get 2. Okay, so the right hand side become the same as what the left hand side, which is 1. Okay, so that's the base step. Then we assume what? The inductive hypothesis. Okay, so we assume what? K greater than or equal to 1, such that P of K is the sum. Okay, so here we just replace the n by k. Okay, we just replace the n by k. Okay, that's what we mean. So our P of k becomes 1 plus 2 up to k equal to what we have on the right hand side of the equal sign. Okay, we know that P of k is true, and we are required to show that the next step, that is k plus 1, okay, is also true. P of k plus 1 is what? Also true. So let's see. So we want to deduce the conclusion part of the inductive step. Okay, so our k plus 1, P of k plus 1 will be what? 1 plus 2 up to k plus the next step, k plus 1. Okay, then on the right hand side, you just replace k by k plus 1. You replace k by what? K plus 1. So when you do that, you get k plus 1 multiplied by k plus 1 plus 1, all divided by 2. I know that k plus 1 plus 1 is what? K plus 2. Okay, so that's what we have on the left hand side of the equal sign. Okay, so now you see, when you compare P of k and P of k plus 1, when you compare P of k and P of k plus 1, you realize that all these terms, that's the sum from 1 up to k, okay, is given by what we have on the right hand side. That is k plus 1 multiplied by k, or divided by 2. Okay, so in P of k plus 1, we can replace all these terms by P of k. Okay, the left hand side, the right hand side of what? P of k. Okay, so you can replace all these terms by what? K plus 1, or divided by 2. By then the next step is what? The next term is what? K plus 1. Okay, so we have k plus 1 divided by 2 plus k plus 1 equal to what we have on the right hand side of the equal sign. That's this one. Okay, now on the left hand side, we express k plus 1 divided by 2 plus k plus 1 as a single fraction. And how do we do that? You see, k plus 1 is divided by 1, so we find the LCM of the denominator. So LCM of 2 and 1 is 2. Okay, so now let's simplify. 2 goes into 2, 1. Multiply 1 by the numerator, you get k plus 1, plus 1 goes into 2, 2. Okay, you multiply by the numerator, that's 2k plus 1. Okay, equal to what we have on the right hand side of the equal sign. Okay, so now let's consider the left hand side of the equal sign. Okay, you realize that, you see, we have two terms on the numerator. We have k plus 1. The other term is 2 multiplied by k plus 1. You realize that k plus 1 is a common factor, so we can factorize k plus 1 out. Okay, so when we factorize k plus 1 out, on the first term we are left with what? K. Okay, that's what we have here. And on the second term we are left with what? 2. That's what we have here. Wow. So we realize that the left hand side of the equation is equal to the right hand side of the equation. Okay, this indicates that our statement is what? True. That's if P of k is true, then the next step, that's P of k plus 1, is also true. This is very, very interesting, right? So since the left hand side of the equation is equal to the right hand side of the equation, therefore P of k plus 1 is what? Also true. Okay, let's move on to the next example. Wow, we also have another interesting question here. We have to prove by induction that n squared minus n is divisible by 2. Okay, n squared minus n is divisible by 2. Okay, so now let's choose any positive integer. Okay, so let's choose 6. We know that 6 is what? Divisible by 2. Yes, because 2 can go into 6 without a remainder, right? And also, 6 is also what? A multiple of 2, right? So since from here we can say that every real number or every natural number, we are dealing with natural numbers, that is divisible by 2. It means that that natural number is also what? A multiple of what? Of 2. Okay. So from the question, since n squared minus n is divisible by 2, then we can say that n squared minus n is also what? A multiple of what? Of 2. I hope this is clear. Right. So now let's begin our proof. Okay. So first step, that's what? The base step. So you choose the first natural number, which is 1. Okay. So for n equals to 1, that's the first natural number. We have what? Okay, we were given n squared minus n. So when you choose n for 1, we get what? 1 squared minus 1. And we know that 1 squared is what? Is 1. Then 1 minus 1 is 0. And 0 is what? Divisible by what? By 2. 0 divided by 2 is still 0, right? It's still 0. Now let's assume k such that p of k is equal to what? K squared plus k squared minus k, sorry. Okay, so we assume that p of k is k squared minus k is what? Also divisible by 2. Okay, so since p of k, which is k squared minus k, is divisible by 2, then we have to deduce that the next step, that's p of k plus 1 is also what? Divisible by 2. Okay, so you just replace k by what? K plus 1. Okay, so therefore our p of k plus 1 is given by k plus 1 all squared minus k plus 1 is what? Divisible by 2. All right. So now let's expand. Okay, let's expand k plus 1 all squared. Okay. So k plus 1 all squared is what? K squared plus 2k plus 1 minus k minus 1. Okay. So when we simplify this, you get k squared plus k. Okay. So here we can create and destroy. Okay, we can introduce plus k and minus k. Okay, so we have k squared plus k can also be written as k squared plus k minus k. Okay, then we can group them. We can group k squared and minus k. Okay, so when we do that, we have k squared minus k plus k plus k. That is k squared minus k plus 2k. Okay, but from the statement, we know that k squared minus k is divisible by 2. Okay, k squared minus k is divisible by 2. Okay, and since k squared minus k is divisible by 2, then we can say that k squared minus k is what? Also a multiple of 2. Okay, so we can write k squared minus k as what? 2p. Okay, where p is what? A natural number. Okay, so we can write k squared minus k plus 2k as 2p plus 2k. Okay, 2p plus 2k. 2 is a common factor, so we can factorize 2 out. Okay, so when we do that, we get 2 multiplied by p plus k. Okay, and 2 times you see p is a natural number, k is also a natural number, multiplied by 2, you will definitely get what? Natural number. And we know that any natural number multiplying by 2 is also what? Another what? Natural number. Okay, and that number is also what? Divisible by 2, since it is what? A multiple of 2. Okay, so from this analysis we can see that p of k plus 1 is what? Also divisible by 2. Okay, and therefore P of k plus 1 is what? Is true for every natural number. Okay, for every natural number. You can pause your video and try the third question. Okay, you are to prove that 2 exponent n is less than n factorial for every n greater than or equal to 4. Okay, you are to prove that 2 exponent n is less than n factorial for every n greater than or equal to 4. Okay. Now let's solve it together. So let's begin with the base step. Okay, this time round n is what? Starting from 4. Okay, so we choose what? 4 for n. Okay, so when we do that, we will get 2 exponent 4 equal to 4 factorial. Okay, and 2 exponent 4 is 16. 4 factorial is 24. Okay, that's 4 times 3 times 2 times 1. That's 24. And this clearly indicates that 16 is what? Less than 24. Okay, that's for base step. Okay, so the base step is what? True. Now let's assume the inductive hypothesis. Let's assume k, okay, such that P of k is less than k factorial for every k greater than or equal to 4. Okay, so we have 2 exponent k less than k factorial. Then we want to deduce the conclusion part of the inductive step. Okay, that's we want to deduce that P of k plus 1 is also true. Okay, P of k plus 1 is also true. So now we just from P of k we replace k by what? K plus 1. So when we do that, we get 2 exponent k plus 1, and we know that 2 exponent k plus 1 is the same as 2 multiplied by what? 2 exponent k. That's from the laws of what? Indices, right? And this should be less than k plus 1 all factorial. We are just replacing k by what? K plus 1. We are replacing k by k plus 1. Okay, so we have 2 times 2 exponent k less than k plus 1 factorial. Okay, but you see, when you have n plus 1 factorial is the same as n plus 1 times n factorial. Okay, it's the same as n plus 1 times n factorial. And this is also the same as n plus 1 n, then n minus 1 factorial in that order up to what? Up to 1. Okay, so for instance, when you choose 6 factorial, 6 factorial is the same as 6 times 5 factorial. At the same time, the same as 6 times 5 times 4 factorial. This is what I mean. Okay, very good. So now k plus 1 factorial is the same as k plus 1 times k factorial. Okay, and let's compare the two inequalities. You see, since 2 exponent k is less than k factorial, okay, and for every k greater than or equal to 4, okay, for every k greater than or equal to 4, this 2, which is multiplying 2 exponent k, is clearly less than k plus 1. Okay, so when you choose 4 for k, you have what? 4 plus 1, which is 5. Okay, and clearly 5 is what? Greater than 2. Okay, and since 2 exponent k is less than k factorial, and 2, which is multiplying by 2 exponent k, is also less than k plus 1, then we can say that 2 exponent k plus 1 is also what? Less than k plus 1 times k factorial, and therefore p of k plus 1 is also true. Okay, thank you very much. I am Mentor Godfred Kudia, a graduate and a teaching assistant at the Kwame Nkrumah University of Science and Technology, Department of Mathematics. Don't forget to like and subscribe to my YouTube channel. Thank you.